Hello, Math Analysis. This is a review of sections 4.3 and 4.4. So in this chapter we are studying graphs. A graph is made up of vertices, which are points, and edges, which are the segments that connect into the points. One of the things that you need to understand how to do is how to determine the degree. Another word for it is variance at each vertex. So you look at the number of connections that are coming into the vertex. So that is a degree of 2. This has a degree of 3. This has a degree of 2, this has a degree of 4, and even though this is one edge, it comes into the vertex in 2 spots, so we count that twice, so that has a degree of 5. One of the things we talked about is the word adjacent. So what it means for vertices to be adjacent is that they are connected by an edge. So if you look at A and B, they are connected by an edge, so I would say A and B are adjacent. One of the things that you need to know how to do for the quiz is to make an adjacency matrix. So you would alphabetize your vertices and put them in a matrix, and I'll just go through and show you how to do this. So let's start with A. A does not have a segment drawn back to itself like E does, so there is no A to A. There is 2 connections from A to B, so I would put a 2 in this spot right here. There is no connections from A to C, there are no connections from A to D, and there are no connections from A to E. So why don't you take a minute and see if you can do the rest of that. Okay, so if you check out this adjacency matrix, see how you did. If you sum the rows or the columns, what you end up with is the degree of the vertex. Okay, in this chapter we talked about connected graphs versus complete graphs. A connected graph means that there is an edge between each pair of vertices, which means that you're able to get from one vertex to any other vertex in the graph. So everything you're looking at right now is a connected graph. If I were to add an extra vertex out to the side right here and it's not have an edge leading to the other vertices, that would be not connected. Or I could have a graph that is just entirely has a second part of the graph that is not connected. To be complete, remember, means that every vertex is adjacent to every other vertex. This is a complete graph with 3 vertices. A complete graph with 4 vertices would be to draw an edge from each vertex to every other vertex. This is a K4, and if we do a K5, you know, as you do this, it ends up, when you're all done, and it looks like a pentagon with a star inscribed in it. So one interesting thing to note is you will know that the degree at any vertex of a K graph is always 1 less than the number of vertices, because you can never connect to yourself. Okay, we talked about something called an Euler path and an Euler circuit, so we're going to take a look at that next. Okay, this is the answer sheet to the class exit slip yesterday. So what it means to have an Euler path is it means that you can take your pencil and you could trace over the graph. So I'm going to draw a graph on the side here and hit every edge exactly once, but you're going to return to the place that you started. So if we have a graph like this, so let's check the degrees. We have 2, we have 4, we have 3, we have 3, and we have 4. What we learned is that to be an Euler path, that there must be exactly 2 odd degrees, and here we have them right here. Those will be your starting and ending vertex. So I start here and I could go, move around in this graph, and I will always end up at the other odd vertex. So to be an Euler path, they're all even but 2. To be an Euler circuit, what happens is that you can start and end at the same vertex and hit every edge along the way, and we know we have an Euler circuit when all of the degrees are even. So I'm going to erase the writing on this here. I can tell that they're all a degree of 4. So it doesn't matter where I start with an Euler circuit, I could start wherever I want. It will allow me to move around that shape and return to where I started. And if a graph has more than 2 odd vertices, then it is neither an Euler path nor an Euler circuit. The last thing we're going to talk about is a digraph. The di stands for directional. It's a graph where the edges have arrows. Think about them as being one-way streets. So we don't just talk about the total degree, we talk about how many ins, which would be edges that are pointing into the vertex, a vertex has versus how many outs. So if I go around and I check this out, there's 2 ins and 2 outs here. I have 1 in and 1 out, and I have 1 in and 1 out. So if I wanted to know if this was an Euler path or an Euler circuit, it's based on the same premises, that if the degree is completely even at each vertex, then that would mean that you have an Euler circuit. But when we talk about a digraph, it's not just that it's an even degree. You would have to say that to be an Euler circuit, the in degrees has to equal the out degrees. So when I look at this, all the in degrees do equal all the out degrees. That means that I'm possible to find an Euler circuit. It doesn't matter where I start, but I do have to follow the directions of the arrows. So if I go against the direction of the arrows, it's not going to work. And you'll notice that we ended where we started. Okay, I'm going to add one more edge into here, and when I add one more edge, it doesn't matter where I put it. I just want to turn this graph into an Euler path. So let's say I do an arrow right here. So that makes this one has an extra out, and this one has an extra in. And that's what we learn about an Euler path digraph, is that all of the vertices have the in degree equal the out degree, except the start vertex. The start vertex will always have one more out than in. So in this example, my starting vertex will be C. He has one more out than in. The ending vertex will always have one more in than out. It just so happens in this example that they both have 1 and 2 and 2 and 1, but that not necessarily is the case. So for example, if I said that we were at a vertex and there were 7 ins and it was going to be our starting vertex, how many outs would it need? 8. And if our ending vertex had, let's say, 11 ins, how many outs would it need? 1 less, which would be 10. All right, there you have it. The only other thing we have to talk about is how to make an adjacency matrix for this sort of a graph. So really quickly here, I'm only going to do a couple letters. Let me put A. I'll just do it for A because class is about to start. So does A have an edge that goes to B? It does. So there's 1. Does A have an, does A have an edge that goes to itself? No. Does A have an edge that goes to B? Yes. Does A have an edge that goes to C? It does not. C goes to A. Does A have an edge that goes to D? It's this guy right here. It does. And does A have an edge that goes to E? And, we don't even have an E in here. All right. Got to go to class. Hope that helps. Study for the quiz. See ya.